Consider this problem. At a point 200 feet from the base of a building, the angle of elevation to the bottom of a smokestack is 35 degrees, whereas the angle of elevation to the top is 53 degrees. Find the height S of the smokestack alone. In problems like this, it's often helpful to draw a diagram. It'll help us to understand the problem, and it'll help us understand the nature of our solution. Here's a diagram of this problem. Now, here's the building, here's the smokestack. Now, notice 200 feet away, the angle of elevation to the top of the building is 35 degrees. The angle of elevation to the top of the smokestack is 53 degrees. All right, I've labeled the height of the building as A, and the smokestack itself is S. Now, we might look at the problem, and by the way, this would be a good time to copy the problem and try the problem on your own and then come back and roll the tape, because you end up pondering these diagrams a little bit to decide what we're going to do next. And when you go through that pondering process, you understand that, gee, we have a right triangle situation here. And in right triangle situations, we have our three trig ratios available. We're going to use the information about this lower side. You see, and we're going to use these angles involved. And the side opposite those angles are these sides. You see, and we have the smaller triangle that has to do with the height of the building, and we have the larger triangle that has to do with the height of both the building and the smokestack. So what we're going to end up doing is finding the height of both the building with the smokestack, and then we'll find the height of the building, and then we'll take the difference between the two. It doesn't matter which one we find first, whether it's the building or the building and the smokestack, but at any rate, we're just going to find the difference of the two. Okay, so let's do that. If we are talking about finding the height of the building first, then we're dealing with this little right triangle, and the angle here is 35 degrees. So we're talking about a 35-degree angle here, and we're talking about, from that perspective, opposite side over adjacent side. Aha, tangent. So it's the tangent, then, of the 35-degree angle is equal to the opposite side, A, over 200. Multiplying by 200 on both sides, we can calculate A as 200 tangent 35 degrees. And using the calculator, we find A to be approximately 140 feet. All right, now for the building with the smokestack, we reason this way. Now, once again, it's the opposite side and the adjacent side that we're dealing with, so that's the tangent notion, or cotangent. But I'm using tangent here if for no other reason than the idea that I'm going to have the unknown quantity in the numerator of my fraction. So I've got tangent, then, of 53 degrees is, now, this total distance on the opposite side is really A plus S. It's the sum of these two. So it's A plus S over the 200 feet. And now the distance A plus S is equal to 200 times tangent 53. And approximating this, we find that total height to be approximately, and I should use approximation here, 265 feet. Now, the idea is to take the difference between these two. Now, the difference between these two, as you can see, is approximately, I think it's 125 feet. 125 feet, approximately, is the height of the smokestack. Consider this problem involving a spring. Suppose we have a spring and we have a bit of weight on the end of the spring. And suppose I grab the weight and I pull it down just a little bit, maybe to a point like this, and I let it go. Well, we know that the spring will pull the weight up and it'll go above this beginning level, you see, and it'll come up here and it'll stretch back down and up and down and up and down. And under an ideal and somewhat theoretical circumstance where we take friction completely out of the whole idea, this weight will return to this lower level every single time, and it'll return to this highest level every single time. And this point of equilibrium, this sort of balancing point here, will be right in the middle of those two. This is called equilibrium, this level right here. And this notion of this oscillating affair is what simple harmonic motion is all about. That's what we want to talk about here. Okay, so we have this weight going up and down. Now, the distance that we have associated with this weight, as I pull it down, I am displacing its position from this point of equilibrium. And that displacement, this distance, it's related to amplitude. Now, the amplitude is the absolute value of the maximum displacement. We say absolute value because we might think of this as a negative and that's a positive, but at any rate, it's absolute value because we're talking distance. Okay, so that's the amplitude in this situation. Now, period has to do with time. We're going to relate, when we talked about sine and cosine functions before, we had the period was an interval over which we had one complete cycle. Well, that interval is going to be an interval of time here in our study of harmonic motion. All right, so we have the idea that the period is the time required for one complete cycle of this weight going from one position to another and then back to the original position. And we have a new word, a new idea associated with this whole cyclical affair, and it's the notion of frequency. Frequency is the number of cycles in one unit of time. Now, frequency and period are highly related to one another, and in a very simple way. Frequency is 1 over the period, and if we solve this for p, we find that the period is 1 over frequency. Now, let's concentrate on period and frequency just a little bit more. And I want to use another example for this. It has to do with wave action. Suppose we have waves on the ocean, and let's say that they're going past us like this, either this way or this way. So we have the waves going past. And we have a buoy or cork or something that's floating that's on the waves. And it's not moving this way or this way. It's just moving up and down. And we're just kind of watching it move up and down. You see, we have this same situation with that weight on the end of the spring. Now, the equilibrium point would be the point where the buoy would float if there were no waves. If we had a calm sea, you see, we would have a point right in between the bottom of a trough, the trough between two waves and the top of a wave. It would be right in between those two. Okay, so that's equilibrium. Now, let's talk about period. Period is the time required for that buoy to go from any particular position all the way through a complete cycle. If we're thinking of a position at the bottom of the trough between two waves, then it's the time it takes for it to go to the top of the next wave down to the bottom of the trough again. Okay, and I'm thinking theoretical here. I'm thinking that all of these waves are exactly the same size as one another, and they're moving at exactly the same rate of speed. Okay, simple harmonic motion. All right, now, suppose the period involved with our buoy is a period of 3 seconds. It takes 3 seconds to go from that position at the bottom of the trough between two waves all the way to the top and down back to the bottom of the trough. 3 seconds. Now, what's the frequency? How frequently, you see, does this cycle occur is what frequency is all about. Frequency is 1 over period. Period is 3 seconds. So the frequency is 1/3 of a cycle per second. Now, let's twist it around. Let's go from frequency to period. Suppose we have a frequency that is 6/10 of a cycle per second. What about the period? What is the period associated with this? Well, we use our relationship. Period is 1 over frequency. Frequency is 6/10. Now, this is 1 divided by 6 over 10. You see, or 1 times 10/6. That's 10 over 6. Reducing, we get 5/3 or 1 2/3. So the period is 1 2/3 seconds. You see, the period, the time over which one complete cycle occurs, is 1 2/3 seconds.